There is a star so large that if you replaced our Sun with it, you wouldn't be reading this, you wouldn't exist. Earth, Mars, Jupiter, all of it swallowed whole, absorbed without ceremony into something so enormous that the word enormous stops working. And the unsettling part isn't the scale. The unsettling part is that we almost missed it. It sits hidden in a corner of the sky, dim and cold and ancient, quietly defying every rule we thought governed how big a star can get. Scientists have a name for the boundary it shouldn't have crossed. It crossed anyway. That's where this goes. But to understand what that means, what it really means, we have to start somewhere smaller, somewhere that feels safe. Because the way the universe dismantles your sense of scale isn't all at once, it's gradual. And by the time you realize what's happened, you're already in too deep. Start with Earth. You already know its big continents, oceans, weather systems that span thousands of kilometers. A jet traveling at cruising speed takes roughly 20 hours to circle it. That's not nothing, but the moment you pull back, even slightly, Earth stops being large and starts being a rounding error. From the Moon, it's a marble. From Saturn, it's a pixel. From the edge of our solar system, the Voyager probe, the most distant human-made object ever launched, Earth disappears entirely into the background noise of sunlight. And the Sun? Our Sun? From where we stand, it looks dominant. It governs our entire existence, our seasons, our biology, our calendar. Its radius is roughly 700,000 kilometers. If you shrunk it to the size of a standard soccer ball, Earth would be a 2-millimeter peppercorn sitting about 24 meters away. The Sun contains 99.86% of all the mass in this solar system. Every planet, every moon, every asteroid and comet and frozen rock, everything adds up to less than 0.25% of what the Sun already is. And yet, the Sun is average. Statistically, cosmically, embarrassingly average. There are stars that make it look like that peppercorn. To understand how that's even possible, you need to understand how stars work, not the simplified version, but the real mechanics, because the real mechanics are what make the story strange. A star begins as a cloud. A vast, cold, diffuse cloud of hydrogen gas and dust drifting through space. Gravity begins to pull it inward. As material falls toward the center, it accelerates. As it accelerates, it compresses. As it compresses, it heats. Eventually, the core becomes hot enough around 10 million degrees Celsius that hydrogen atoms begin fusing together. Two hydrogen nuclei collide with enough force to overcome their mutual repulsion, fuse into helium, and release an enormous amount of energy in the process. This is nuclear fusion. This is what a star is. That energy radiates outward in all directions, creating pressure and outward push against the inward crush of gravity. When these two forces balance, the star stabilizes. Astronomers call this hydrostatic equilibrium. It sounds clinical, but what it actually describes is a permanent, ongoing explosion being perfectly contained by its own weight. A star is a controlled catastrophe. It is, in the most literal sense, barely holding itself together. Now, here's where the structure of the universe starts to show itself. Not all stars are the same mass. Some form from denser clouds, collapse more violently, accumulate more material, and mass changes everything. A more massive star has stronger gravity, which compresses its core more intensely, which accelerates the rate of fusion, which generates more energy, which forces the star to expand outward. More massive stars are larger, hotter, and this is the part that matters far more unstable. Astronomers have mapped this relationship using what's called the Hertzsprung-Russell Diagram, developed independently in the early 1910s by Danish astronomer Ejnar Hertzsprung and American Henry Norris Russell. It plots stars by temperature on one axis and luminosity, raw brightness, on the other. When you map thousands of stars this way, a pattern emerges. Most stars fall along a diagonal band called the main sequence. This isn't a location in space, it's a category of behavior. Main sequence stars are fusing hydrogen in their cores. They're in equilibrium, they're stable, at least for now. Our Sun sits comfortably in the middle of that band. It's a G-type star, medium temperature, medium brightness, medium mass. It will live for roughly 10 billion years total, and it's about halfway through that lifespan. Reliable, steady, unremarkable. But look toward the upper left corner of the diagram, hotter, more luminous, and the stars become something else entirely. A star like Bellatrix, the left shoulder of Orion, burns at around 22,000 degrees at its surface. That's nearly 4 times hotter than our Sunday. It's 8.5 times more massive. And the consequence of that mass, the consequence of all that gravitational compression, is a fusion rate so violent that the star's volume swells to 200 times that of our Sunday. Bellatrix is not unusual for its class. It is, in the context of upper main sequence stars, fairly typical. But the cost is staggering. Bellatrix has been burning for 25 million years. It has approximately 7 million years left. A star like our Sun will outlive Bellatrix by a factor of more than 1,000. The most massive stars are simultaneously the largest, the brightest, and the shortest lived. They burn through their fuel at a rate that makes their existence almost fleeting on cosmic timescales. This is why they're rare, not because they don't form, but because they're gone so quickly that the odds of finding one at any given moment are low. There is a theoretical upper limit to how massive a main sequence star can get. Around 150 times the mass of our Sun, the outward radiation pressure becomes so intense that the star begins to blow itself apart. The energy generated at the core is so extreme that it overwhelms the inward pull of gravity. Beyond this limit, a star can't hold itself together long enough to meaningfully exist. And yet the universe, as it tends to do, found a way around this. When 2 massive stars in a binary system spiral inward and merge not through gradual accretion, but through actual collision, the result violates the rules. The combined mass, the residual momentum, the complex dynamics of the merger produce a star that shouldn't exist by normal formation pathways. This may be the origin of R13601. R13601 sits in a star-forming region called the Tarantula Nebula inside a satellite galaxy called the Large Magellanic Cloud. It is not just the most massive star known to science, it may be the most luminous object of its kind in the observable universe. Its estimated mass, approximately 265 times that of our Sunday, its radius, around 40 times larger. These numbers don't have a clean analogue in everyday experience. There's no metaphor that makes them feel real. At a certain scale, the mind simply stops converting data into sensation and starts treating it as abstraction. R13601 belongs to a class called Wolf-Rayet stars. We've identified around 220 of them in our galaxy. Scientists estimate there may be as many as 2,000, but they are difficult to find, and their lives are brief. Wolf-Rayet stars are not young stars in a stable phase. They are massive stars in an advanced, deteriorating phase, burning through the last of their available fuel, shedding enormous quantities of mass in dense stellar winds that move at up to 3,000 kilometers per second. Every million years, R13601 ejects roughly 10 solar masses worth of material into space. It loses weight the way a star loses everything violently, continuously, and without slowing down. R13601 releases as much energy in 4 seconds as our Sun produces in an entire year. If you account for all its radiation, most of which is ultraviolet, invisible to human eyes, it outshines our Sun by a factor that language struggles to hold. And it will only exist for approximately 3 million years total. We are observing it during a window that, in cosmic terms, is barely a frame. But here's what no one tells you about mass and size. They are not the same thing. R13601 is the most massive star known. It is not the largest, not by radius, not by the measure that actually captures what big feels like when you try to imagine standing inside a star's atmosphere and looking outward. There are stars that are less than a fraction of R13601's mass that stretch across space on a scale that makes R13601 look compact. This is where the story takes a turn most people never see coming. Stars don't stay the same their entire lives. The main sequence, that stable band on the Hertzsprung-Russell diagram, is only one phase. It's the long, quiet middle of a star's life. What comes before is chaos. What comes after is transformation. And the transformations that stars undergo in their final stages produce the largest objects in the known universe. Here is what happens. A star like our Sun spends billions of years fusing hydrogen in its core. Eventually, the hydrogen runs out. Without the energy generated by fusion, there's nothing to push back against gravity. The core begins to contract, not explosively, but steadily, relentlessly, driven inward by the star's own weight. As it contracts, it heats. It heats until the temperature crosses a new threshold: helium fusion. Helium atoms, the ash of hydrogen burning, now become the fuel. But the energy released by helium fusion doesn't just ignite the core, it heats the surrounding shells of the star layers of hydrogen that were previously too cool to fuse. Suddenly, fusion is happening in the shell as well. The star is generating energy in two places simultaneously. The outer layers, now superheated, expand dramatically, rapidly, on stellar timescales. The star inflates like something waking up. This is a red giant. Our Sun, in approximately 5 billion years, will expand to a diameter of roughly 300 million kilometers. Its current diameter is about 1.4 million kilometers. That expansion factor, more than 200, will bring its outer edge close enough to consume Mercury and Venus, and possibly Earth. The same Sun that fits into the background of our sky will fill it completely. Will be everything. For a brief time in its final phase, our Sun will be a giant. But a red giant is not the largest thing a star can become. For stars with more than 8 times the mass of our Sun, the process continues. The core collapses further after helium runs out, reaches temperatures sufficient for carbon fusion, then neon, then oxygen, then silicon. The star burns through progressively heavier elements in successively shorter time frames. What took millions of years with hydrogen takes only thousands with helium, only centuries with carbon, only years or months with the heaviest elements. The star is accelerating toward its own end. And, as this happens, the outer layers, no longer supported from below, expand even further. The star becomes a red supergiant. These are the true giants, not by mass, not by luminosity, by sheer physical dimension. Betelgeuse is one. You've seen it. It's the bright red star in the upper left of Orion, visible to the naked eye from anywhere in the northern hemisphere on a clear winter night. Its diameter is approximately 1.2 billion kilometers. If you placed Betelgeuse at the center of our solar system, its surface would extend past the orbit of Jupiter, Mercury, Venus, Earth, Mars, all interior to the star's photosphere, all inside it. Jupiter itself would be submerged. The 4 rocky planets and the first gas giant, all consumed. And Betelgeuse, despite that, is not the largest. Hold on to that. This becomes important. There is a star, dim, distant, cold by stellar standards, sitting in a corner of the constellation Scutum, the Shield. It has been observed for over a century. It has been catalogued and measured and argued over by astronomers who can't quite agree on exactly how large it is, because measuring something at a distance of 5 to 10,000 light-years introduces uncertainty that compounds with every variable. The star is called WOH Scuti. Inside WOH Scuti, you could fit approximately 5 billion suns. Not 5 billion Earths, 5 billion suns. The number is so large it doesn't produce a clear image in the mind. Try anyway. The Sun is already 1.4 million kilometers across. Multiply that diameter by roughly 1,700. That's WOH Scuti. Place it at the center of our solar system and its surface would extend past the orbit of Saturn, possibly beyond Uranus, depending on which measurement you trust. Neptune would still be outside it. Barely. It is not particularly hot. Its surface temperature is about 40% cooler than our Sun's. It glows a deep, dark red. It is not bright enough to see with the naked eye despite being one of the most physically enormous objects in the galaxy, Because its energy is spread across such a vast surface area, and because it sits so far away, you would need binoculars or a small telescope to find it. A red supergiant at the far end of its evolutionary path, approaching something it cannot survive. Scuti is between 10 and 20 million years old. It likely has only a few million years remaining, and in those final stages, it will actually shrink. Not collapse, not yet, but transform. The outer layers, no longer sustainable in their current state, will begin to shed. The star will blow off enormous quantities of material mass equivalent to an entire Jupiter-sized body in a single violent outburst, and it will do this many times. As it sheds mass, it contracts. As it contracts, it heats. Eventually, it becomes something called a yellow hypergiant, a different kind of enormous, one that trades physical size for luminosity, burning hotter and brighter before the final collapse into a supernova. Those ejected shells, the material flung off in the final convulsions of a hypergiant's life, are not wasted. They mix with existing dust clouds in the surrounding region. They seed interstellar space with carbon, oxygen, nitrogen, iron. They provide the raw ingredients for new stars, new planets, and eventually, after billions of additional years of chemistry, the conditions necessary for life. What you are made of was forged in something like this. Not Scuti specifically, but its ancestors. Stars that lived and died before our Sun even formed. There is something worth sitting with in that. Now, the boundary that Scuti is approaching, the one that defines how large a star can physically grow, has a name. The Hayashi Limit. It is a theoretical line on the Hertzsprung-Russell Diagram marking the maximum radius a star of a given mass can achieve. It isn't arbitrary. It emerges from the physics of convection inside stars, the way heat moves from core to surface. When a star expands too far, the temperature difference between the core and the outer layers becomes too extreme to maintain efficient energy transport. Convection takes over completely. Gravity begins to win. The star is forced to contract. Scuti is near that limit, perhaps at it. It cannot meaningfully grow larger than it already is. And here's the part that unsettles researchers who think about this carefully. If the Hayashi limit is real and the physics behind it is sound, then Scuti may represent something close to the actual ceiling of stellar size in the observable universe. Not just the largest star we've found, the largest star that can exist. Unless we're wrong about something. There is a star outside our galaxy, outside the Milky Way entirely, that forces the question back open. It sits in the Large Magellanic Cloud about 160,000 light-years away. Its name is WOH G64. It is one of only a handful of stars outside the Milky Way that we've been able to image directly with any meaningful resolution, and what recent observations suggest about it is strange. Over the past decade, it has grown dimmer. Not gradually measurably dimmer in a time frame that suggests it has already begun the transition from red supergiant to yellow hypergiant. It is shedding mass. It is shrouding itself in its own expelled material. It may already be in the final sequence before collapse. But the measurements of WOH G64's size are uncertain. At 160,000 light-years, the margin of error in angular diameter becomes significant. Some estimates suggest it might rival or even exceed Scuti. We genuinely don't know. The instruments we have aren't quite sharp enough at that distance to resolve the question clearly. This is the kind of uncertainty that astronomers live with constantly. Not the clean uncertainty of incomplete theory, but the frustrating uncertainty of insufficient resolution. The universe is too large and our eyes are too small, which raises a question that most people never think to ask. We have catalogued hundreds of thousands of stars. We have mapped their positions, measured their spectra, estimated their masses and temperatures and distances. We have built diagrams that describe their entire life cycles from birth to death. We have done all of this using light electromagnetic radiation that travels from those stars to our instruments, carrying information encoded in wavelength and intensity. But light is limited. Dust absorbs it. Distance dilutes it. Entire regions of our galaxy are obscured behind dense molecular clouds that block optical wavelengths entirely. We see the universe through a narrow set of windows, and we have built our models of stellar physics around what those windows allow us to see. The largest stars we've found are the largest stars visible to us. That is not the same thing as the largest stars that exist. If there are star-forming regions in the Milky Way or in galaxies we observe at lower resolution where extraordinary stellar mergers have produced objects larger than UY Scuti, hidden behind dust or simply too far away to resolve properly, we would not necessarily know. The universe does not announce its exceptions. It keeps them until our instruments improve enough to find them. There is also a deeper possibility, one that the data doesn't rule out. The stars we understand are the stars that fit within our current models of stellar evolution, but models are constructed from observations, and observations are limited by what we can see. When astronomers first encountered Wolf-Rayet, stars objects that seemed to exceed what stellar physics predicted, they spent decades arguing about how they could exist. The answer, eventually, was stellar mergers. A pathway that standard models didn't emphasize until the evidence forced it. What other pathways exist? What other configurations of mass and energy and time produce objects that don't fit neatly into the Hertzsprung-Russell Diagram? What categories of stellar object are we missing because we've never had an instrument powerful enough to detect them? We don't know. And the absence of knowledge isn't comforting here, because the history of astronomy is a long series of discoveries that expanded the known range of what exists almost always upward, almost always towards something larger or more energetic than expected. Every time we built a better telescope, the universe revealed something we hadn't anticipated. This pattern has repeated itself so consistently that treating it as coincidence seems naive. The largest star we've found is enormous beyond useful description. It sits near the boundary of what physics says is possible. It will be dead within a few million years, leaving behind a black hole or a neutron star, an object smaller than a city, containing more mass than the Sun, the extreme opposite of everything UY Scuti represents. The same material compressed by gravity into something so dense that space itself curves around it. From a star so large it could contain 5 billion suns, to an object smaller than most mountains on Earth in a few million years. The universe doesn't just build giants. It destroys them completely and replaces them with something so different that the connection between the two seems almost impossible. That transformation, what exactly happens during the collapse, what forces dominate, what remains after a star of this size dies, is a question with answers that get uncomfortable the longer you sit with them. The physics of what happens in the final seconds of a supergiant's life are not fully understood, the models diverge, the simulations don't all agree. And what they disagree about isn't a minor technical detail. It's the fundamental question of what kind of object emerges from the death of the largest things in the universe. That's the thread that doesn't close here. That's the question worth carrying forward. Because the size of a star is one thing. What a star becomes, what it leaves behind, what those remnants do to the space around them, what they mean for everything in their vicinity, that is something else entirely. And that is where the real strangeness begins.